Thank you, Pierre, and the other organizer for this nice workshop. My name is Marco Ginoni. I'm from University of Milan. And my talk is at the border between quantum metrology and quantum control, as you can see probably from the title. And I'd like to start with one slide of motivation. So the starting point of this project was the fact that in quantum metrology, they say that we should get a quantum enhancement if we use quantum resources to estimate parameters, the so-called Heisenberg limit. But then there are some no-go theorems that say that this quantum enhancement is lost as soon as you get some interaction with the environment, as soon as you have some noise. And our intuition is that if you have access, or at least partial access to the environment, you should be able maybe to restore this enhancement. And the reasons are two. The first one is that if you monitor the environment, if you can measure this environment, you should get maybe some information on the parameter you want to estimate. And the second reason is that by monitoring the environment, also you typically also purify the system. So this is the motivation, and this is the outline of my talk. I will start by giving a very brief introduction on two topics: continuously monitored quantum systems and quantum estimation. In particular, I will start with basic quantum estimation, and then I will describe quantum estimation with time-continuous monitoring. Then I will address our parameter estimation problem, which is quantum frequency estimation and in the presence of noise, and I will conclude with our results and some summary and conclusions. So time-continuously monitored quantum systems. So I will use the standard input-output scenario in quantum optics. We have our quantum system, can be a qubit, can be an oscillator, and this system interacts with a train of harmonic oscillators. We are assuming that we're assuming that the environment is Markovian, so this A input T has this canonical commutation relation delta correlated in time. And we assume that there is a generic interaction Hamiltonian between the system described here by the operator C and these input operators. And then we have the output operators. And we know that, that if we don't measure these output operators, then we can describe the dynamics of the system by means of Markovian master equation. So this is the so-called unconditional dynamics, where we have this dissipator here that depends on the operator appearing in the interaction Hamiltonian. While if we put a detector here, we have so-called unraveling of the master equation. And depending on the detector, we can have infinite different unravelings. For example, if we put a homodyne detector here, then the output would be a classical photocurrent. So it depends on the average value of C plus C dagger, depending on which kind of quadrature I'm measuring here. And we have a linear increment here in the photocurrent. And the system evolution is described by a stochastic master equation, where the first part is just the usual dissipative part, and then we have a nonlinear term that depends on the measurement we are performing. And the effect of the measurement is described by this linear increment here. If we change, for example, detector, we can assume that we put a photodetector on the output, then the measurement result will be the quantum jump, so just 0 and 1, depending if we see a photon or not. And we have a different stochastic master equation. This is the one for photodetection. We don't have a linear increment, but a Poisson increment that takes value between 0 and 1. And again, its average value will depend on the conditional state of the system. So these are basically the three things we are going to use later. So the unconditional dynamics and the conditional dynamics for homodyne and photodetection. So quantum estimation theory. Typically, quantum estimation theory can be described by using a three-step protocol. The initial preparation of your quantum system, so you prepare the probe in a state ρ0. Then you have an encoding of the parameter, which is typically a CP-TP map. that depends on this parameter omega that we want to estimate. And finally, a measurement. And quantum mechanically, this measurement is described by a P of M operator. So the whole measurement process then is described by a conditional probability of measuring x, the result of this final measurement, given the value of the parameter omega. Then everything is classical here. We have a classical probability distribution. And classically, there is a Cramer-Rao theorem that says that the variance of any possible unbiased estimator I can build from m repetition of this experiment, of this measurement strategy, is lower bounded by 1 over m, the number of experiments, the number of measurements. So this is just standard central limit theorem term. And times f, which is the classical Fisher information that depends on this conditional probability here. And we also know that at least asymptotically, for large enough m, there are some estimators that are efficient. It means that this bound can be achieved. Quantum mechanically, we can do something more. We can basically optimize over all the possible P of M operators. And we obtain this more fundamental bound that basically depends only on the state after the encoding and not on the P of M, of course. And basically, the Fisher information is replaced by the quantum Fisher information. And again, at least in the single parameter scenario, we know that this bound is achievable. It means that there is at least a P of M such that the corresponding Fisher information is equal to the quantum Fisher information. So this is standard quantum estimation theory for one parameter. But here we are interested in something a little bit different because our encoding of the parameter, during the encoding of the parameter, we have some time continuous monitoring happening. So the encoding now is described by a conditional map that is conditional on this time continuous output that I called here YT. And after the encoding condition on this output, we have, again, we can think again to perform a final strong measurement on the conditional state. And here the measurement process is described again by a conditional probability of measuring for each experiment this continuous output and x for the final measurement given the parameter omega. And the question you can ask, okay, what is the correct quantum Cramer-Rao bound in this case? And so the idea is that you have two sources of information on omega if you use this kind of measurement scheme. On one side, you have the information coming from this output, and this can be quantified by this classical Fisher information. And you can calculate this classical Fisher information by following what is described in this paper by Gammenmark and Molmer. So the idea is that you can consider the evolution of the anormalized state here, that this is a solution of the linearized stochastic master equation. And the idea behind this is that the trace of this anormalized state is related to the likelihood of the conditional probability of measuring this output. And then that's why you can basically calculate the Fisher information by using this formula. And so this is one source of information. The second source of information is the final strong measurement on the conditional state. So at time t, so at the end of the monitoring, you have a conditional state and you can perform a measurement. And so and the amount of information you can get on the parameter is quantified by this quantum Fisher information. And this is the formula we used later in our results. That depends basically on the eigenstates and eigenvalues of rho c and on the derivative of rho c respect to the parameter omega. Okay, now how you have to combine these two quantities to get the correct Cramer-Rao bound, and this is the answer. So this is the new quantum Cramer-Rao bound where you have what we call an effective quantum Fisher information, which is the sum of the classical Fisher information of the continuous output plus the average of the quantum Fisher information of the conditional states over all the possible trajectories. So this is the figure of merit that we want to look at later in our results. This was derived, for example, also in this paper by Katana and Guta. We re-derived again in this other paper last year. And the same similar equation with different operational meaning of this probability here can also be found in other contexts of quantum estimation for Bayesian Cramer-Rao bound or for quantum metrology with post-selection. Okay, actually, we can think that we can do something even more complicated, because in the scheme I've shown you so far, we are fixing the measurement strategy apart from the final strong measurement, but we are already saying that, okay, we are doing time continuous homodynamic detection on the output modes or time continuous photo detection. But in principle, you can think that you can perform any possible measurement on the state of the system and environment, which for initial, if the initial state is pure, then at any time this state will remain pure. So this corresponds to perform also non-local in time measurements on the output operators and so on. And actually, you can also derive this fundamental bound that optimizes over all these possible generic POVM. And this, again, was derived in this paper by Gammemark and Molmer. And as you can see, so this is the formula, and depends on this rho bar, which is the solution of this generalized master equation. This is for an Hamiltonian parameter. So the idea is that instead of having the commutator between h and rho, you have left and right depending on two value of the parameter omega 1 and omega 2, and then you use this omega 1 and omega 2 in these derivatives here. So what I want to stress is the fact that this ultimate bound depends only on the unconditional evolution, as we expect, because this is the, and then because you are optimizing over all the possible things you can do given the unconditional evolution. So finally, you have this hierarchy of inequalities. This here is the quantum Fisher information of the unconditional state. So what you will get if you have a noisy dynamics and you perform a strong measurement at the end. And we already know that this is upper bounded, but what we have called the effective quantum Fisher information. So if we perform some time continuous measurement on the output and then a final strong measurement in the conditional state, and this is because of an extended convexity property of the quantum Fisher information that was proved in these two papers. Then what we have just said is that this effective quantum Fisher information is upper bounded by this ultimate quantum Fisher information that optimizes over all the possible measurements I can perform on system and environment. And so one question is, can we reach optimality by using this sequential monitoring? And the final inequality is the fact that, of course, if we don't have noise, the quantum Fisher information is larger than this ultimate bound. So, and in the following, we are going to look at these inequalities and see when we can replace equal or strictly lower in between the different figures of merit. Okay, quantum frequency estimation. We have the usual setup. Now, the probing system we consider is made of n qubits. We start by considering the, so let's now suppose that we have an unitary encoding described by this Hamiltonian. So the parameter we want to estimate is the frequency omega, and basically it corresponds to the rotation frequency along the z-axis of the total spin. And what we already know is that if we start with a classical separable initial state, for example, a spin coherent state, the quantum Fisher information is standard quantum limited, so grows linearly with n. If we prepare a GHZ state, an entangled state of superposition of 0, 0, 0 plus 1, 1, 1, 1, then you can achieve the Heisenberg limit. So we have a quadratic behavior of the quantum Fisher information in n. So this is the ideal case. What happens if we put some noise? In particular, if we consider independent noise on each qubit. So now the encoding will be a tensor map of, this map acts equally on each qubit. And what you will see is that the quantum Fisher information in this case is not anymore monotonous in time, and it's better to rewrite the quantum Cramer-Rao bound in this form. Basically, you want to optimize to minimize the variance of the estimation omega given a total time of the experiment t. You divide this total time by so basically you have m number of experiments, t is total time, big T is the total time, small t is the duration of the single experiment. And you keep fixed this big T, and you can optimize over Q over T, over the quantum Fisher information over the monitoring time. So this is the quantity we want to optimize in the noisy case. And so in the literature, there are a couple of no-go theorems that say that if this map, this encoding is a full rank channel for the qubit, then asymptotically you lose any quantum enhancement. You're back to the standard quantum limit. And this is for any non-zero value of the noise. So as soon as you get some noise on interaction with the environment, asymptotically you lose any quantum improvement, any improvement in the scaling. You can still get a constant factor, can be also high, but you can't get any improvement on the scaling. So let's now consider some examples. We are going to focus on Markovian independent noise. So this is the master equation for the n qubits. And now we have sigma alpha here, which is our collapse operator. And we are considering two cases, alpha equal to z, so the parallel noise, or alpha equal to x, transverse noise. So for parallel noise, you can derive analytically the quantum Fisher information of the unconditional state. This was done in 1997 by Wege and collaborators, and you get this standard quantum limited behavior. Still, as you can see, you have kappa here, which is corresponds to the noise. If kappa is small, then this can be really high, so you can get a constant enhancement, but still you can't get any Heisenberg scaling. For transverse noise, you don't have a full rank channel, and you can see that by optimizing over the monitoring time, then you can get an asymptotic scaling between standard quantum limit and the Heisenberg limit. Still, you can't get n squared, but you can get something like n to the 5 over 3. The thing here is that you are optimizing over time, and basically this optimal time will depend on the number of qubits you have in your probing system, and this optimal time will decrease to 0 with n. Okay, this is the this is the first example, at least up to my knowledge, where they show how to circumvent this no-go theorem. There are actually other ways, by using quantum control, quantum error correction, by looking at different kind of time inhomogeneous dynamics. And in general, for example, okay, if you measure, in some sense, the environment, and you perform some feedback after that. Typically, all these approaches work in the case of transverse noise. So if you have dephasing parallel noise, there is no example, at least up to my knowledge, where you can get Heisenberg scaling. And our approach is, okay, let's continuously measure the environment and without feedback, and let's see what we can get. And this has been proved to work at least for a single-step dynamics and for dephasing in this paper by Katana and Gutta. And then it's also been proved to work for collective transverse noise. Here, the goal was a little bit different, because collective transverse noise is not detrimental for the Heisenberg limit. But what was shown in this paper is that if you start with a coherent spin state, so with a separable state, and you perform this continuous monitoring of the collective spin, then you can achieve Heisenberg scaling thanks to the spin squeezing that is generated during the dynamics. So anyway, here is exactly more or less the same approach, but not in a continuous time fashion, and for only the phasing. And here was a little bit different, but still these kind of measurement schemes seem to be useful. Okay, this is our strategy, our measurement scheme. So we have n qubits, and we assume that we are able to prepare them in a GHZ state. We are going to look both at parallel, so dephasing or transverse noise. And we are assuming that each qubit can be monitored, the environment, the independent environment for each qubit can be monitored continuously in time. And we're looking both at the case of homodyne detection or photodetection. Then we have a conditional state time t, and we perform a strong measurement on this conditional state. And then we are going to look at these inequalities here and try to answer to this question. Can we reach the Heisenberg limit? Is the measurement scheme optimal? And also, what is the role of monitoring efficiency? So for parallel noise, so when the collapse operator is sigma z, the calculations are quite simple, thanks to the fact that also for the conditional state, the whole dynamics happens in a Bay-dimensional subspace, at least if you start with a GHZ state. And so we were able to calculate analytically this ultimate quantum Fisher information. And this is probably looks trivial, but we'll discuss this later. We obtained that if you assume that you perform any possible measurement, system and environment, you reobtain the unitary result. So the Heisenberg scaling can be reobtained. Now, with our time continuous strategy, in particular with photodetection, we show that if eta equal to 1, so if we have ideal photodetection for all the qubits, then you can, then is optimal. So this, you get equality here, and then you get, again, the unitary result. So this is, at least, as I was saying before, the first example where you can show that you can retrieve, in some sense, the Heisenberg scaling by using this, also in the case of dephasing. And the nice thing of this result is that you don't get any information on the parameter on the time continuous output. So the Fisher information here is equal to 0. But thanks to the monitoring, basically you keep track of the conditional state of the n qubits. And you see that, for example, this is the conditional state after m jumps, quantum jumps. Is still, this is still in a GHZ state form. And so because of this, you can still obtain a Heisenberg limited quantum Fisher information. Now, what happens if we have inefficient detectors? So if eta is smaller than 1, then unfortunately, you're back to standard quantum limit. And if you look at the formula, it's really similar to what we have seen before for the unconditional state, but where basically you have kappa, the dephasing rate, replaced by an effective reduced dephasing that depends on the efficiency. So for you, this means that if eta is lower than 1, you can still get a constant enhancement that can be also arbitrarily high near for eta approaching to 1. Okay, this is for parallel noise. The extra bonus of this approach is that thanks to the symmetry of the GHZ state, you don't really need, I mean, in the picture I've shown you before, there are n independent detectors for each qubit. But thanks to the symmetry here, you don't really need to have these n detectors. And you don't need to know from where the quantum jump has arrived. You just need to know that there has been a quantum jump from one of the qubits. And this at least relaxes a little bit the requirement for an future experimental implementation of these schemes. And this will be true also for any input state with permutation symmetry between the n qubits. So for transverse noise, we don't have much symmetry, in particular for the conditional state, so we need to use the full exponentially large Hilbert space. But likely, we have been able to calculate analytically this ultimate bound. And the good news is that we have n squared term here, so you can still get some Heisenberg behavior in the quantum Fisher information. But the bad news, but I was quite happy because I think it's not a trivial result, is that this is not equal to the unitary case. So even if you're assuming that you can perform all the possible measurement system and environment, the fact that the encoding Hamiltonian and the noise do not commute, because of this fact, some information on the parameter is lost during the dynamics. So you get something that is always lower than n squared t squared. Then we have, well, this is strong numerical evidence that for ideal photodetection or also ideal homodyne detection, our scheme is optimal. So by using this sequential monitoring, so you don't need to do something really complicated to get this result, you obtain the optimal, you obtain Heisenberg scaling and this optimal quantum Fisher information. And again, you can optimize over time, the optimal time as done for the unconditional state. And the other good news is that this optimal time doesn't go to 0 anymore for n going to infinity, but goes to a constant that can be also derived analytically. What happens with finite efficiency? We can't make strong claims, but we have some numerics both for photodetection and homodyne detection. And these plots are for different monitoring efficiency. The black dashed line here corresponds to the optimal ultimate bound, and this dashed dot line corresponds to the unconditional quantum Fisher information. And of course, by changing the efficiency, you go from one limit to the other. Eta equal to 0 corresponds to the unconditional dynamics, eta equal to 1, as we said before, to the optimal quantum Fisher information. The other thing is that for homodyne detection, you have a linear behavior of the quantum Fisher information asymptotically, while for photodetection, this will go to 0. Of course, you can see also that there is always a maximum of Q over T over the monitoring time here. And if we look if we plot this maximum as a function of n up to n equal to 7, this is as much as we could get with our numerics. Basically, you see that, as you expected, is between the unconditional behavior that goes as n to 5 over 3 and the Heisenberg scaling that goes as n squared. But as I said before, we can't really claim anything about the scaling for eta smaller than 1. For sure, is not classical, so is between these two values. And also for the optimal time, we can't really say if this goes to 0 or it remains constant for any value of eta. Okay, so this is just a summary of results. We have shown that the Heisenberg scaling can be restored by monitoring the environment, at least with ideal detectors and without feedback. So this is just by continuously monitoring the environment. For parallel noise, you get exactly the Heisenberg limit. For transverse noise, some information is lost, but you get some quadratic behavior in n. And we have shown that these schemes are also optimal. So if you assume that you can perform any measurements on system and environment, you can't do much better than sequentially monitoring the output modes and then doing a strong measurement in the conditional state. And again, I think this is a non-trivial result. We have also some, I think, interesting technical results that we were able to evaluate analytically these ultimate quantum Fisher informations. And also, we have developed a stable and versatile algorithm for the numerical evaluation of this effective quantum Fisher information. And if you're interested, we made the code available on GitHub. Again, just the take-home message is that we proved the intuition that monitoring the environment is useful and you don't need feedback. You have to be careful to look at the correct quantum Cramer-Rao bound where you look at these measurement strategies. And now we are looking at many possible generalizations of this scheme. For example, looking at more realistic input states, not GHZ state, but for example, spin squeeze states that can be more or less generated in the lab. looking at ancillary system not affected by the Hamiltonian and by the noise. What happens for many body Hamiltonians where you have also these so-called super Heisenberg scalings and many body dissipators, and also for in the multi-parameter case where you have some non-trivial problems due to the non-commutativity of operators in quantum mechanics. So the quantum Cramer-Rao bound is not always achievable in that case. Maybe time continuous monitoring can be also thought as a tool to circumvent all these other no-go theorems. I would like to thank my collaborators, Francesco Albarelli, who is a PhD student at the University of Milan, Matteo Rossi, who was a PhD student in Milan, now is at the University of Turku, and Dario Tamascelli, who is assistant professor at the University of Milan. And I think that's it, and thank you very much for the attention.